Oh. Okay.
Hello, doctor.
Okay. Hello.
Entering.
All participants. Thank you for correction or fixing the problems. So we will start now our presentations. So we have first. I want to ask all of them are here or not. The paper number 52 is here or not? I think no. Paper 19.
I'm here.
Okay, very good. So I think you will start the first one because the author of the 52 said that they have problem with the traveling from the work to home and so on. Paper 8 is here. Hello? Your microphone are muted. Paper 8, Mario Alfredo Ibarra Carrillo. Alfredo. Jesus Molina Lozano. Yeah, no, well, okay, maybe they will come later. So 18, Maria de Los Angeles, here. Don't respond. Alberto Maldonado.
I'm here.
Okay, 42 and 33, Dante Mujica Vargas. Okay, I think here is here. So let's start our presentations. Time is running. So because we have now the first presentation, author of the first presentation, we started with the presentation 19, similarity and dissimilarity functions, cosymmetry property, a focus on probability distributions. It will be presented by Maria Elena and Sastegi Ortega. Please, Maria Elena. Okay, we see your presentation. You can start. You have 10 minutes for presentation and 5 minutes we will have for questions, please.
Okay, can you hear me?
Yes, we can hear you. We can see your presentation also. Thank you.
Okay, I'm going to type similarity and dissimilarity function, cosymmetric property, a focus on probability distributions. This is my table of contents. Had an introduction, methodology, results, and conclusions. Similarity and dissimilarity measure used for different data types in pattern recognition, machine learning, and decision making. We can use distance like Euclidean, Manhattan, Chebyshev, Minkowski, cosine. But probability distribution are important data types used in pattern recognition and machine learning. For this reason, the definition of distance measure for probability distribution and analysis of their properties attract much attention. By example, the following paper had more than 2 dozen citations. A comprehensive survey of distance similarity measured between probability density functions. The negation of probability distribution. Jagger introduced the concept of negation of subjective probability distribution. Suppose we have a probability distribution hike price, modeling human prediction of the stock price. How do we present the probability distribution corresponding to the not high price? Jagger proposed the following definition of the negation of PD. P equal to P1 to Pn, where Pi equal to P of Xi equal of the set of outcomes X equal to X1 to Xn. The negation of P is equal to the negation of P1.
Sorry, maybe not necessary to read formulas. Yeah, we can see them. Thank you. Okay.
Okay. Okay. The negator is as we can see, the negator of P is equal to this formula, where Jagger introduced on this paper on the maximum entropy negation of probability distributions by IEEE. An involutive negation of probability distribution. Operation involutive, it means that when we apply the function at the same function, we obtain the same P. By example, the negation of P is equal to P. And the last example, we have the negation of high price. But in that case, we can obtain that this was equal to high price. And that means that this operation isn't involutive. And the operation involutive is important because the Dr. Hilar introduced the property cosymmetric. The negation of P is equal to the negation of P1 to the negation of Pn, donde the negator is equal to max. Well, like I see on that formula. For distance between probability distribution, the distance between P and Q with involutive negations, such that the negation of P, as we can see, the distance between the negation of P and the negation of Q is equal to the distance between P and Q. That means that satisfies the property cosymmetric. And that was introduced by Patrichin and in the contracting and involutive negation of probability distributions. When we are working with a probability distribution, we have to talk about their properties. A probability distribution, the value is between 0 to 1, and the sum is of HP pi is equal to 1. And we are working with the similarity function. That means that they satisfy the property of symmetry and irreflexivity. The symmetric is like commutative in the real numbers, and irreflexivity means that the distance of P is equal to 0. And now we introduce the cosymmetric property. That means that the negation of P between the distance between the distance between the negation of P and the negation of Q is equal to the distance between P and Q. By example, if we take probability distributions, and we have the negator introduced by Patrichin, to understand how the negation function works on the set of probability distribution, since the sum of the elements of the probability distribution must be 1, the negation of P over probability must be 1, the negation of Q, which the sum of its elements also with 1 when applying the formula for each of the elements of the probability distribution. As we can see, if we had P and apply the negation of P, we obtain 0.3, 0.2, 0.25, 0.1, 0.15, and we had that sum 1. And when we apply the negation of these results, we can obtain P. That means that is an involutive operation. To make your analysis, we make use the average of the distance of P and Q, and some on the distance of the negation of P and the negation of Q. We work only with the distance Euclidean, so Ergel, Sorensen, and Jacquard, and Disset. And it was easy to prove that when when we apply that formula, we can obtain new dissimilarity measure that satisfies the properties to be a dissimilarity function. We construct a dissimilarity matrix for each of the distance that we make and the originals. And to analyze like them, we create a scatter plot that compare the distant originals and the new distance, and we use the dendrograms to know how is what is the similarity between the distance. A distance matrix describes a pairwise distinction between M objects, and it's a square symmetrical M by M matrix with the each element equal to the value chosen measure of distinction between ITH and the JTH object. And a dendrogram are especially useful in cluster analysis, where similar data are grouped into set called cluster. The cluster two elements are in a dendrogram. It means they have a greater similarity. Here we have the new distance, applying the formula. We have a new distance called Euclidean coaverage, Sorensen coaverage, and this coaverage. This distance satisfies the property of cosymmetric, and also they are dissimilarity function. And then we create a data set composed by 1 to 1,000 probability distribution, each with the trials where the sum each vector is equal to 1, because they are probability function, and they have a uniform distribution. And then we proceed to create this distant matrix for one of them, and then we transform the matrix that we obtain a matrix 1,000 by 1,000, and we transfer it into a vector the size 1 by 1,000. With these vectors, we create scatter plots to compare the different distance. and then we create dendrograms. As we can see, the distance with greater correlation, because we calculate the correlation between the distance. We use the Pearson correlation, and we obtain with the analysis of the scatter plot. In yellow, we can see the distance with greater correlation. As we can see, the distance with greater correlation, if we compare the distant originals with the distance news, it was distant Jacquard versus distant Euclidean coaverage. But also distant Jacquard versus distant Dichet coaverage had a great correlation. And if we compare the distant originals versus the distant originals, we obtain that the distant Jacquard versus the distant Dichet had the great correlation. And if we compare the distant news versus the distant news, we obtain that the distance with great correlation is what distance Sorensen coverage with distance Sorensen coverage. Now in that figures, we can see the scatter plots that show how they had the correlation. If we can see, when we find a linear, I don't know, when the correlation is linear, is like a linear, they had a bigger correlation. And with the dendrograms, we can find that the J-card, when we compare the distant originals versus the distance original, the distant J-card, the distant Schwarzschild, the dendrogram says that they have a greater correlation, and the distance Sorensen with the distance DC. And when we compare the distance news versus the distant news, we can see the greater correlation is Euclidean coverage versus DC coverage, and Schwarzschild coverage versus J-card coverage. And when we compare all of them, we obtained that the distance Schwarzschild versus J-card had great correlation, and the distance Sorensen versus J-card coverage, and the distance coverage versus the distance Euclidean. But if we can see the result obtained with the analysis of the dendrograms and the analysis with the scatter plot, it's a little different because we obtain the distance had different correlation or similarity. As a conclusion, a method was introduced to create a new distance to comply with the cosymmetric property. Several methods are also introduced to analyze the similar discrete distance, also original ones and themselves. As I see, the distance and I can conclude that they had more correlation is the distance DC and the distance Euclidean. Why? Because when we was made in the analysis, we can see that with the scatter plots and with the dendrograms, the distance Euclidean had what similarity or correlation with the distant coverage, even when other distances like J-card and Sorensen had greater correlation, but they have only great correlation in one of the analysis. Like if we compare the same distance with the new distance with the new distance, or the original distance with the original distance, but when we compare all of them, we can find that the distant coverage had more correlation with the distant Euclidean in one of them analysis. And this was the bigger conclusions. And if we had been a great correlation, the distance Euclidean with distance DC, we can say that we can use a distance DC coverage to like we use a distance Euclidean. As a future words, in the title we can say we will talk about similarity and dissimilarity function. However, we only work with some similarity function because some reviews suggest make it shorter, and also some of them distance are dual. So in the future we plan to do more extensive analysis on similarity functions that were not mentioned here, like cosine, cosine or Ricicca. In the past, we worked with domain of real numbers. Now we're working on probability distribution, but we plan to work to other domains such as fuzzy sets. And what's the object of work with this similarity and dissimilarity function and create new? And it's because we would like to create new association measure. That means that we can create new functions like person correlation, Kendall correlation, and that was introduced by Batirchin. But this will be our future works. And here we have some reference, and thank you.
Thank you so much. So we have time only for one question. If somebody have questions, please. Okay, no questions. So I think really the results can be interesting because we just, as you found, that cosymmetric, new cosymmetric measures very highly correlated with known distances, but satisfy additional property like cosymmetry, which is important if you try to use these distances in models of probabilistic reasoning. Okay, but I see that it needs more detailed analysis of the results. Thank you so much. So if you have no more questions, please we go to the, you can go out from the presentation, Helena, thank you.
Okay.
We now the next paper is number 8, systolic tensor core to speed up arithmetic calculations. Mario Alfredo Ibarra Carrillo, Jesus Yalia Montiel Perez, Jeron Marino Lozano. Somebody is here or not?
I am here. Touching the window.
Okay, what is your name, please?
Mario Alfredo Ibarra.
Ah, okay, it's primero, please. You can
Okay,
start.
let me see. Okay, thank you for inviting me to this event. My lecture is Systolic Tensor Core to Speed Up Arithmetic Calculations. I'm a student of Computer Research Center, and my advisor is Dr. Jesus Yaja and Dr. Elon Molina. Okay, I will present you context, state of art, and my solution and some results. My context is about autonomous transport. There are three kinds of these vehicles. The first is boats. Once the boat is loaded, the captain runs the very autonomous boat. I don't know if today the boats continue crashing. The second vehicle is about planes. Once the plane is in the air, the plane can follow a route. And in the case of possible crashing, the planes can negotiate between them and alter the route. The third class is special interest is about cars, autonomous vehicles. The streets are the most complex environment. For our autonomous vehicle, there are other cars, there are traffic signals, traffic lights, pedestrians, bicycles, motorcycles. It is not important what kind of autonomous vehicle be. The amount of information that is passed to the computer is amazing. So we need special devices called calculation accelerators. One of them is vector engines. Let me focus. At the beginning was Pegasus, and today is the processor Orin. This is the center of this target. Orin can reach 2,000 teraflops of power processing. As I remember, this is a vector engine. This vector engine is performing dot product in several number of stages. The other is the tensor processing unit. This is a systolic matrix. The product I'm showing the screen is a product of Google. How it functions, okay, this is a small model. At the left, this is a matrix A, the rows of matrix A, and in the top, there are the columns of matrix B. So in every clock cycle, the system is performing the multiplication. Well, of course, we have other papers. We have investigations. About investigation, there are the convolution engine. Let me focus. Okay, a convolution engine consists of a matrix of multipliers, and therefore are transport to other tree. This is the the convolution engine I'm showing is so big, 100 multipliers. The way this machine can function is using a fixed point data format. This is a special model. It contains a memory writer with a decoder. The decoder drives the package, data package, to a particular collection, and every collection has a communication port, a router, the convolution engine, a folder, and a programmable activation function. This is for neural networks. This is a special device. It's another kind of device, the fourth kind of device. This is a dream machine. And you can see points. Every point is a set of registers and a MAC multiplier accumulation circuit. And you can see it is possible to configure several routes, several circuits. Every circuit is able to evaluate a neural network. We use this dream was never implemented. So this is my entry point. I take some parts that can be implemented, make an evolution, present a result. This is one part of this dream machine, and let me focus here over in the left. We have 4 circles. White circles are processor elements. However, they only consist of registers. The black circle contains register and a MAC, accumulation circuit. At every clock cycles, data are transported between the circles, and in the black circle, the arithmetic operation is performed. A MAC operation is performed. In the right side, we can see what is happening. The purpose of this device is to multiply this row vector of features with the vector, with this column vector of weights of a neuron. We have an evolution. In this case, we have 2 black circles. And so the device can multiply a vector of features with 2 columns of weights of weights about a neural network. It is not important how many columns of weights I add. The time in which the multiplication is performed is always the same. I have another exercise. In this case, I will multiply 2 rows of features with one column of weights. I'm performing the operation. You can see at every clock cycle, the circuit is operating. It is not important how many rows I add. The number of cycles in which the operation is performed is always the same. Okay. It is necessary to blend these exercises, the ability to multiply columns with the ability to multiply rows in only one circuit. And I have the circuit that perform all that operation. This matrix can perform a matrix multiplication, in this case, 4 matrices of size 4. This device consists of, sorry. Okay, this device consists of 4 rings, horizontal rings. Every horizontal rings are transporting features. We have 4 vertical rings, and every vertical ring can carry weights of neural networks. And this is I'm showing the contour. Every element of this matrix has its own contour, so I have a lot of models controlling the device. This is a very complex device. Okay, as a way to prove my device, my proposal of solution, I've I built this device. Okay, in the first step, I have to get a data set. At the step 2, sorry about the Spanish. I have a computer making the training of a neural network. In the third step, I will use a data set for testing. In the step 4, I will use a computer for testing my neural network with my test data set. And in step 5, I will use my device as a calculation accelerator. This is FPGA is my device.
Sorry. Please, can you all of you mute your microphones because we cannot hear well this presentation. Sorry, you can follow with your presentation, please. No, we cannot hear you. Please unmute. Maria Alfredo,
Yes.
please.
Yes. I have the control.
Thank you.
Okay. Okay. I'm showing a device used to test my propose. I use 2 computers. The first computer is used to train a neural network. The second computer is used to evaluate this neural network. The result of this second computer is important because the result will be used as a reference, or comparison reference. The purpose is to use my propose, also calculation accelerator, compare the results obtained by my computer with my calculation accelerator. I have some results. Okay. This is a commercial. A single processor can perform a matrix multiplication of size 4 and powered by 3 clock cycles. The vector machine, like the NVIDIA, can perform the same operation in this quantity of cycles. This is logarithm. The systolic matrix, like the Google, can perform the same matrix multiplication in this quantity of cycles, and my device can perform the operation in n cycles. Using numbers, matrix multiplication of size 4, vector machine can perform the operation in 12 cycles, the systolic matrix in 9 cycles, and my device can perform the operation in 4 cycles. Using a frequency of 50 megahertz, the vector machine can perform 267 million of operations per second. The systolic matrix reaches 356 operations, and my device can reach 800 million of operations. However, in practical terms, my device is the reunion of Raspberry Pi and the implementation on an API. The Raspberry Pi has to perform tasks as encode data provide coming from the TensorFlow, make packages, send the packages to the FPGA and control the FPGA. This task takes some time. The used language was Python. So
sorry, you have 1 minute, please.
Okay, that is enough. Thank you. My theoretical result for 1 core is near 0.1 second. However, the theoretical time is 20 microseconds. I've implemented two cores. I have a reduction of time. Well, some reference. As a conclusion, okay, the use of Python as a language to manage data takes time and reduces the advantages of my device. Well, this is a set of reference consulted, and thank you.
Okay, thank you very much. Unfortunately, we could not hear very good because maybe your colleagues also give presentation. So somebody have one question, so we have time for one question. So if no questions, thank you so much. We will go to the next presentation. Please close, thank you. And mute your phone, please. Yeah, thank you so much. Okay, the next presentation which we have is paper number 18. After house here or not? A meta optimizer based on the upper confidence bound algorithm and orthogonal arrays, a preliminary empirical study, Marie de Los Angeles. Somebody here?
Yes, I am here.
Okay, please start your presentation. You have 10 minutes and 5 minutes for questions. Please.
Okay. Let me share my screen. You can see my screen?
Yeah.
Okay. Thanks for the opportunity to be here. And this works. It's about the no free lunch NFL theorem that indicates that not optimization algorithms solve all optimization problems. The above implies that researchers and end users need not only to adapt the selected meta heuristic to achieve a good solution for a specific problem, but also to perform parameter settings tasks every time they face new problems. Parameter settings optimization meta heuristic is a problem for which we propose a solution through a meta optimizer. In this case, wait a minute. Ready. In this case, to analyze this problem, we use the case of study and a disaster scenario where the communication services were interrupted during a disaster, degrading the effectiveness of the rescue teams. Hence, deploying an emergency communication network to provide wireless connectivity is vital for preserving human life. Using unmanned aerial vehicles, USVs, is a potential alternative because it has a low-cost operation, rapid deployment, safe access to dangerous areas, and scalable and flexible deployment. However, the number of services the network provides is directly affected by the location of UAVs. Consequently, it is necessary to optimally locate the UAVs to provide the maximum number of successful communication links on the network. Figure 1 shows our scenario where we need to provide communication services to user in this area. But it's relevant to talk about that evolution strategy, in this case, or algorithm, or meta heuristic algorithm required to be used some specific parameters. For this case, we use a set of layers. In the lowest layer, the optimization problem. The next layer implies the optimization model. And finally, inside of next evolution strategy, and inside of this, the optimization model. And over these layers, the UCV1 algorithm for tuning. To propose the meta optimizer is the proposed meta optimizer is based on UCV1 and an experimental design defined by orthogonal arrays to automate offline tuning. UCB is one of the reinforced learning algorithms to solve the multi-armed bandit problem. And what is this problem? This problem aims to find which machine in a casino will give us the maximum average reward. UCB1 solves the problem as follows. An agent pulls an R from the gambling machine at each time step T to receive a reward. As uncertainty increases, the agent performs exploration, pulling entire R's from the set of gambling machines. And when the uncertainty decreases, the agent pulls the R of a single gambling machine with the maximum average reward. This is the problem that UCB1 resolves. For us, each machine represents a configuration of the meta-heuristic algorithm. UCB has two phases. The first one is initialization. In this phase, all the gambling machines are used. And once we finish this phase, the second is a loop where we try to maximize Q. In this case, QJ is the average reward obtained by each machine. See? And the second, our intention to maximize is the probability of successful voice services for mobile users. This is the reward that we try to find. Thanks. Methods. The methodology to tune a meta-heuristic is as follows in this graph. First one is an orthogonal design where we provide a set of configuration for meta-heuristic. The second step in this methodology is to put inside of UCB1 the entire configuration and relate them with each bandit. Once the algorithm execute the second phase, in this case, the loop phase, they provide the better configuration. In this case, bandit, for this example, bandit 3. This configuration is used to generate the solution to the problem before mentioned. In this figure, we can see the orthogonal arrays to tune the 1+1 evolution strategy. We use 9 configuration. The algorithm has 2 parameters. In this case, the first one is how many iterations must elapse to adapt sigma. Is called, we use it 5, 10, and 20. The second is sigma. Sigma refers to the step size for the algorithm explore the solution space. Each configuration is related with bandit, as we mentioned in the last slides. Our results. The number of execution by bandit, finally, the most relevant configuration was the number 5 here, with the number of execution near of 35 maybe, because I can see the exact number here. And the bandit 1 has the lowest number of execution because was our condition stop in this experiment. Here we can see the performance of each bandit. Bandit 1, as we can see, has performs an exploration behavior, and bandit 5, in this case, has exploitation behavior. As similar behavior has bandit 6, or most relevant configuration in this exercise. Here, this figure shows the behavior of entire configuration, exploration or exploitation behavior here on the set of experiments. Figure 8 shows the average probability of successful voice services. QA for bandit 5, the average probability of successful voice service was above of 0.6 or 60% above of this quantity, while bandit 6 has a different behavior, but we expected that if we execute more iteration, maybe bandit 6 can improve bandit 5, but in this set of experiments, our best result was bandit 5. This is the same result, but trying to show the different perspective. And here we can see again bandit 5 with the shortest number value interquartile range than the other configuration. And the number of outliers is less relevant in this configuration than the rest of bandits. Here, the time on second to provide a solution is more expensive bandit 5 because the rest of configuration stop when there is not a good solution. That's why bandit 5 has the highest time to provide solution. This is no problem. Really, this is the time that a solution, a correct solution, must be provided, different to the rest of the configuration. Finally, in figure 11, we can see the winner bandit. In this case, the configuration number 5, having in the parameters, using the parameters 10 and 0.001 to be used in the finally in the meta heuristic. Our conclusion: these techniques using these algorithms along with DOE technique will provide a technique to automatize the process to tune meta heuristic, and using the UCV1 algorithms, exploration process can provide an early stop, reducing the configuration time for the meta heuristic. Our future work, we plan to use another kind of bandit algorithms. One technique to apply is Thompson sampling, and we are exploring another way another way of stop conditions for the process of configuration. or tuning meta heuristic. That's it, and thanks for the time to be
Okay,
here.
thank you. Thank you so much. So we have time for one question. Somebody have questions? Okay, so you can leave. We have now another presentation, paper number 30, data-driven control of a 5-part parallel robot with compliant joints. Angel Ramirez Martinez, I suppose, will present, or who? Yeah,
I will
I
present.
see. Please load your presentation.
Yeah, thank you. Well, hello everyone. Good morning. Today I'm going to be presenting a data-driven control of a 5-bar parallel robot with compliant joints by me, Angel Ramirez Martinez, and collaborators. Today I will be talking about a brief introduction about 5-bar parallel robots, compliant robots, and some techniques used to control this kind of robots. Also, I will be presenting the controller implemented in this work, the results of the implementation, and the conclusions. First of all, a 5-bar parallel robot is a kind of robot that is a closed kinematic chain, and it is connected to a fixed base and 4 links connected between each other. This kind of robot is widely used due to it provides the robot with enhanced rigidity, dexterity, and accuracy compared to serial robots. Some implementations of these kind of robots are used to do pick-and-place tasks, and more recently, rehabilitation. Also, the difference between this and one implementation in this work is that instead of using common bearing joints, we use flexible joints that gives the system different characteristics of movement, but also represents a challenge in modeling and also in control. Some examples of compliant robots are used mainly in healthcare industry to do minimal invasive surgeries. So, as I was saying, by nature, the 5-bar parallel robots are constrained, and we need to take into account into the model. One example is by Cervantes Culebro and collaborators that he presents his work about a 5-bar parallel robot with compliant links that has 2 flexible bodies that take into account into the model. When he did the model, it arises a 4-degree partial differential equations that by definition, it gives the system an infinite degrees of freedom. So it cannot be solved analytically, and he chooses to solve this by a numerical method. In this case, the one implementation that we did, we had 3 flexible bodies that are the joints, not the links, but it will represent a more complex dynamic system. So in order to avoid this model, some alternatives are doing the model approximation, in this case by a neural network, or also by a model-based controller. It can be approximated by also a neural network that also in the reference 18. So, as I was saying, in this implementation, we use a 5-bar parallel robots made out of aluminum and 3D printed with PLA to do also the assembly, but also to get the markers of the Cartesian coordinates of, in this case, the main part, the end effector of the robot. As I was saying, the joints are 3D printed by TPU that gives the mobility of the robot and gives this characteristic movement instead of common bearing joints. Instead of that, we use TPU and flexible joints. In order to obtain the the position of the end effector, instead of using a model that it is not acquired in this case, we obtained it, but actually measured the end effector. It was by an array of 8 cameras of Bicon and 12 markers on the robot. These cameras usually work at 100 frames per second, but with some adjustments, we end up using at 500 frames per second. So it was the bottleneck of the controller that was working at 2 milliseconds at the sample time. So in order to do that, we obtain and approximate the inverse dynamic model of this system by of getting a neural network of getting the Cartesian position of the end effector. We get the Cartesian position X and the Cartesian position Y, and 14 delays of each measurement. Why to choose 14? We run an experiment and we end up getting different delays at the entries, and we end up with 14 that get the minimum root mean square error, and with a simpler implementation of only 14. If we increase the delays, we get a better result, but the neural network is more complex, so we choose to have 14. The neural network is a one-layer neural network that approximates the inverse model by getting the entry vector, that it is a 14 length vector, that multiplies to a weight matrix W1, enters an activation function, in this case, hyperbolic tangent, and after that, it multiplies with a second matrix of weights, W2. This identification of the inverse dynamic model, it runs online. So if it changes, it also changes the identification that is good to this implementation. So it is the weights are constantly updated by running the adaptation algorithm that follows these equations. When we can see some parts of the neural networks that are the X, that it is the input vector to the neural network, we see C1, that is the result between the entry vector and the first weight matrix. We see Y1, that is the output of the activation function. The matrix A, that is very important because it is a matrix minimization error that needs to be between 0 and 1. And with this, we can update the weights and online identification of the dynamic model. So here's the control structure implemented. The block G is a PID controller that is partially tuned. It does not need to be fully tuned in order to only help us to run the dynamic of the process, and the neural network will obtain the following action in the control. So at the beginning, we don't know the inverse model, but after some sample times, we obtain enough information to do the approximation, and then the neural network can handle the control of the plant. We also can see the block B, that it is a desired behavior of the plant, that in this case, it chooses to be a under-damp behavior in order to have the fastest response of the plant to do the identification. So in this case, the robot was tested against a common bearing joint robot that can see in this graph. The trajectory is set at 1.2 hertz in the task, that it is a semicircle desired trajectory. As we can see in the graph in red, it is the bearing joint robot that cannot follow the reference in comparison to a compliant joint robot. To get a bigger picture of the behavior in both robots, we ran a frequency sweep of the controller, starting at 0.15 hertz and ending at 3.2 hertz at the frequency sweep. We can see that the common bearing joint robot at 1 hertz, it starts increasing the error until at the frequency of 2 hertz, it completely fails and the experiment is ended. And with the compliant joint, we can see that the bandwidth is bigger in comparison to the common bearing, that it starts to behave also with a graded error at 1.2 hertz in the frequency task. But we can see that it tries to return to the reference, but in about 2 hertz, it starts increasing until 3.2 hertz. The experiment is finished. To give meaning to this frequency, we obtain the impulse response of the compliant launch robot in order to get that at 1.2 hertz there is the first vibration mode of the system. So that's why it is keeps increasing the error. It tries to come back to the reference, but at 2 hertz there is another vibration mode that the controller cannot keep going down until it meets 3.5 approximately, where there's the third vibration mode, and that's why the control starts misbehaving completely, because it reaches the 3 vibration modes. So the conclusion is that we obtain a neural network with a finite number of neurons of a virtually infinite numbers of the grid that will need an infinite number of neurons. But in this case, with a finite number of neurons, we approximate an inverse dynamic model. And also with a partially tuned PID controller with a neural network, the output of that controller can be improved. So thank you very much. I will be happy to answer all your questions.
Thank you very much. Somebody have questions, please? So I have some questions about this slide. Yes, you can, with a finite number of neurons. You have neural networks with infinite number of neurons?
No, of course not. We don't have infinite number, but for example, we need to keep increasing the number of neurons. In this case, we only have 30, but if that wouldn't work, we need to start increasing until it identifies the model. In this case, we end up with 30 networks, and without going to 100 or 1,000 networks, that it keeps increasing. It is a kind of a small neural network that identifies a virtually infinite number of degrees of freedom.
Okay, so maybe better to say about restricted number of neurons, something like this is, yeah?
Yeah.
Idea was as well. But also another question, there is another ways to identify the inverse dynamic.
Yeah, of course. We use a neural network because it's a universal approximator, but there's some other techniques to identify and approximate the inverse dynamic model, because by doing this, sometimes the exact inverse dynamic model, it will not be a physical function, but with an approximation, we can approximate its behavior. We can use a different kind of strategies to get the inverse dynamic. Well, we use the neural network to get this approximation of the dynamic system.
But nobody before you used neural networks for this problem?
In this case, for identification of the compliant robot, the fiber parallel robot, I didn't find anything about using neural networks to identify this inverse dynamic to a infinite degrees of freedom system. Okay,
maybe in this case you need formulate, okay, we propose to use neural network for blah, 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 yeah? Because it's you have to do it first time. And or maybe neural network with special property with a restricted number of neurons and so on.
Yeah.
Oh, thank you.
Thank you. Thank you very much.
Presentation. Thank you. So please close your presentation. We have next presentation. It will be number 42. A novel approach quantum key K nearest neighbors algorithm. Alberto Maldonado Romo, Jesus Yalia Montiel Perez, please. Who will present? Alberto. You will present? Hello? Alberto Maldonado, he is not here. Okay, I suppose it's Alberto Alvarado Serrano, sorry. So it seems that the author of this presentation are not here, 42. So we have next presentation, 26, emotion detection in educational dialogue by transfer learning. Aurelio Lopez Lopez and Jesus Miguel Garcia Garasteta, Samuel Gonzalez Lopez. Somebody will present this presentation. 26. No.
And I'm here 42.
42. Yeah. Okay, please present.
Okay, thank you so much. Let me share my screen. I'm
Yeah.
sorry, I had a problem with my internet. Can you see my screen?
Yeah, we see your screen, please.
Okay, you can see my screen. Let me start my
Sorry, but I
presentation.
suppose there was initially 3 authors, no? Or only 2?
No, three. Yeah, I forgot
But
first.
why here are only 2? Sosa, yeah.
Yeah.
Yeah, please.
Okay. So thank you so much for this time. So I will talk about my project, who has the title Novel Approach Quantum K-Nearest Neighbor Algorithms. So first of all, I try to explain the classical ways. Well, in this area, we are talking about for quantum computing and machine learning. So I focus more in this classification problem or classification algorithm. Is like we had different data sets with different classes, and what happened if we don't know a specific data point or different instance, what is the class? So the K-nearest neighbor mentioned we can use certain different distance, like Euclidean distance, Hamilton distance, Minkowski distance, all in the previous presentation we saw. So in this case, depends of the short neighbor or the short number of the neighbors. In odd value, we can obtain the classification or obtain the class. So like in the below part, in the right part, we can see with k equals to 3 and we can obtain the distance. So using this basis idea, I will try to show you a quantum computing algorithm. In this case, we are mention the method or the workflow for this proposal idea is we are initially with a data set. We can explain a train and test set. We are using a pre-processing. The pre-processing using a classical pre-processing, like reduction of the variables, of the variables, non-normalized or normalized, and we're doing a quantum transition or encoding. Like we are using an angle encoding. After that, we are using the quantum approach when we are starting with a quantum run or a Q run with different size, applying a criteria for fidelity estimation or fidelity value, like it's equivalent like the Euclidean distance, apply a like a structure for the algorithm. We call it Grover's algorithm. We are obtain a certain measurement when we are obtain the address, a specific address with high probability to obtain what is the class to obtain for a specific test value or a class we don't have what is the class. So with that, we are obtaining the accuracy. So first of all, what is the classical data? How to combine a quantum data? Well, we can obtain certain characteristics. We are starting with the most popular or basic data set for classification is the 80s data set. We are obtaining integer value, real value. So we can encode all this value in a certain rotation. In quantum computing, we obtain different rotation, rotation Y, rotation X, rotation Z. So in this case, we're doing this rotation and encoding the value in a limitation 0 to p or 0 to 2p to pi. So in this case, we ought the iris data set using in a high value is approximately to pi. So when using this processing, so no chain, no normalized, only using this case. And the quantum random access memory is like we can see in the left part a binary tree when we obtain certain values. In this case, the qubits or the quantum bit we can do in a superposition or in a linear combination. What what that means is we can obtain certain probability, the zero value like one value, and the other qubit the same thing. So we can obtain 1 over square root to the end, multiply the board associated to certain address value. So in this case, the left part is the address and the value it could be other. So we can obtain with 1 over 4 the state 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1. And in other words, the complexity of this binary tree for a quantum approach is the log n. So what is example for a quantum run? Well, in this case, we are working with gates and qubits. In the left part is the number of the qubit, and the approach with the square or the lines with circles is the quantum gates. So we can obtain the quantum address two first with a equality probability to obtain 1 over 4. Obtain, and the other part is the value we want to obtain in encode the value. In this case, 0.2, 1.25, 2.33, and so on is the value we can encode in a certain address. In this case, the address 000111011. After that, we obtain the subtest. We are calling this case, or the equivalent for the Euclidean distance is using 3 qubits or 3 values. The 0 value is the basis. We can obtain a measurement with 2 quantum gates, like the Hadamard thing. And the other thing, like C and phi, is the equivalent with we want encode the information. In this case, the ARIS data says one trend is the phi value, and the psi value is the test or the test value. We don't know what is the class. So the first argument is the parameter we know what is the class, and the second one is we don't know. And when we do a measurement, or is in other words, like the question, we obtain a certain probability, we can identify when it's equal to 1, that means it's practically the same. If it's 50-50, practically so different. So using this format, we obtain with our approach this following characteristic is the number of the address with a certain superposition. We obtain 1 over square root of the n to select certain value for the quantum run, apply all this information for a training set, apply the encoding in the same way with the test set value only 1, apply the subtest, and after that apply the oracle. The oracle is the characteristic we obtain what is the high probability of the similarity subtest distance. In this case, is what is the closest value equal to 100% in the state 0. And all these characteristics with the other part is the complement part is the same architecture to the Grover argument. The Grover argument is as popular arguments to mention. We can obtain for a node data sets format or not structure or unstructured data set, we can obtain a higher probability when we obtain certain information values for interest. In this case, following for the oracle. And the measurement is, in this case, the address for the quantum run. So what happened with that? This is a basic example when we are working in the quantum computing, and the Q0 is the address. So in this case, we're only say the information 0 and 1 address, and we can encode into different values. We apply the Euclidean distance, like using the subtest, and after that, when we are measurement, apply the oracle, and what are a high probability when we are in this case is 0 or 1, the distance we want to identify. And what happened with the measurement? We obtain a binary string because we are convert the quantum data and a classical data, and when there's certain values is the address. In this case, it's a binary address associated with a high probability. We obtain what is the high probability. We can change or do a conversion with the binary string to an integral value, or obtain the what is the most accurate with high probability value, and that is the address, and select with that is the label we can put in the test label, or in the in the test label. And in conclusion, all the information we can obtain, or we do different experiments using the ARIS data set. We had a train set with 105 and test set is 45. And we're using a Q run of size 128, so we're only using under 5, and we are using the classical approach. The classical approach using PCA only for one parameter, or reduce one parameter using the rotation encoding, the rotation C encoding, the rotation Y with PCA, and rotation C with PCA. And we can see we had a good performance with rotation C in using the k-nearest neighbor with 1, 3, 5, 9, and 11 nearest neighbors. So the idea of this is with a certain probability, so it's not a specific approach. So we can do experiment 10 times, and the average of this is this kind of results. Conclusion for this project is we can use in the current, the subtest, and the Roberts algorithm to apply a novel application for the k-nearest neighbor using in a quantum way, and we can obtain a similar results in the best case with 96% compared with the classical way is 97%. So indicate the precision because we are doing a reduction between 0 to pi, or the rotation 0 to pi. We had a good performance, practically the same like the classical approach, and we can conclude our approach is practically the same like a classical way. And this is my reference for my project, and yeah, thank you so much.
Okay, thank you so much. So somebody have questions? No, I have questions. Why you apply this quantum, what you say, technique for the well-known problem of k-nearest neighbors? Yes.
Okay, yeah, the characteristics of this is what happened if we can use quantum computing approach to reduce, it could be the number of the qubits, the number of the parameters, and identify it's possible to obtain at least the same accuracy or a better accuracy in this case of the performance. In this case, with the Q-run, we can reduce the number of the bits or the qubits because we are do like a binary tree reduction of the number of the variables. In this case, with only 3 qubits, we can say 8 address. Like in a classical way, we can say it for 8 address, 8 values. So we are reducing in a log time because the log m is the quantum, but in the classical is n. So we are reducing the complexity space in one thing, and practically we can obtain the same approach or the same results in a quantum way. So we are only using this like a toy model from the IRIS dataset to identify is optimal because we can only use a short number of the qubits. This is like 16 qubits. So we obtain a good performance with 16 qubits compared with a classical way, 16 qubit, that is not even a float value. The float value is practically, we are using 24 bits. So in this case, with 16 qubits, we can obtain a good classification with a practically the same approach like the classical way. And if we can improve with more number of the qubits or with a real quantum computer, we can obtain even with a more complex data set, practically the same reduce, and we can optimize the time and the space.
Okay, thank you. Some other questions? It seems no. Thank you so much.
Thank
You
you.
can leave. So the next presentation, it was number 42, 26, emotion detection in education of dialogues by transfer learning. Some authors of this paper is here or not? Not here, yes, yeah. So 26, we have no presentation 26. And also there was a first presentation number 52, mathematical model of temperature distribution along the length of the old production well. Somebody will present this presentation. Also, no. We have no more presentation. Thank you to all of us. So if you have time, maybe visit some other sessions. Thank you. Bye.
Sorry, my presentation is agended for this session, the number 34.
What number?
34.
34?
Yes.
I don't see, maybe just you say about session number 5?
Yes.
Oh, let's look for what it is out here. Okay. It was maybe added later, no? Okay, please. Yes, sorry. I see. I checked another file. Sorry. Please. So next presentation is 34. Optimized Topsys technique for trajectory selection of self-driving vehicles on highways. Who will present this presentation? Dante Mojica Vargas or somebody else?
The speaker is Andres Arenas. It's me.
Okay.
So
Okay, Andres Arenas, please. Sorry, I just checked another file. You can start.
yes. Can you see my
Yeah, we can
screen?
see. Yeah.
So greetings to all attendees. Today I'm going to present the work titled Optimized Topsys Technique for Trajectory Selection of Self-Driving Vehicles on Highways. The authors of this work are Dante Mojica Vargas, Arturo Rendon Castro, Antonio Luna Álvarez, Birna Rincón, and your speaker, Andrés Arenas. So the contents of this presentation are introduction, background, the method we propose, experimental results, conclusions, and future works, and for last, the references. As a brief introduction, all of us who have driven a vehicle on a highway can identify with the situation in the image, where we have different alternatives to steer the vehicle, some better than others. But how can we be sure that we are choosing the right one? As human beings, our experience can help us to answer this question easily. But in the case of self-driving systems, it's not so easy to determine. And it is precisely this problem that this work was focused. The objective was to develop a method that allows us to perform the planning and selection of the most appropriate trajectory with the use of human experience. In order to achieve this, it's necessary to go to certain concepts. The first is path planning. As we can see in the diagram, the process starts in the perception module. It's here where the information from the outside of the vehicle is collected through various sensors. From this module, we can obtain the parametric curve, which describes the geometry of the road, as well as the initial and final states, which are points on the global route. To facilitate the localization of the different objects present in the environment of the vehicle, we have resorted an alternative reference system, which can integrate the geometry of the road as an element of it. In this case, we use different frame. In this space, the fifth-order polynomials can generate the different trajectories that detect the movement of the vehicle in the longitudinal and lateral axis. In addition to that information, we need to know the steering angle, which is obtained by the means of the Stanley control model. All these generate a tuple of trajectories, which contains information of the velocity, acceleration, turning angle, and longitudinal and lateral position. In addition to this information, we felt it was necessary to include more criteria in order to make a more informed decision. So we use the following: the distance from the ego vehicle to the rear vehicle, the relative position of the vehicle to the center of the line, the braking gap, and the number of lane changes made by the trajectory. This is done in order to facilitate the understanding of the driving dynamics for the trajectory selection algorithm. The decision-making technique we use is Topsys, which is a multi-criteria decision-making method that uses a W vector of weights and I vector of impact as an inference system to evaluate each criterion of the tuple of the trajectories. In the following diagram, the algorithm uses as input the tuple generated by the path planning algorithm. Then a normalization is applied, so we can use the weight vector to each criteria, and with the configuration of the impact vector, an ideal best and ideal worst is computed.
Then the distance of each path are measured to obtain the positive and negative distance. This distance indicates how close or how far the paths are of the ideal solution. Finally, a score is obtained for each path, and the path with the highest score is selected. As we observe, this method uses vector W and I as mechanisms for transferring experience. And as we will know, not everyone has the same driving experience and preference. Therefore, we decide to use 3 sets of weights and impacts to define 3 different driving styles. The conservative style reflects a driver with little experience, who maintains a very low speed, performs fewer maneuvers, and stays in a single lane. On the other hand, the moderate style portrays the experience of a more experienced driver, who seeks to maintain an optimal braking gap and stay in their lane with a fear of making maneuvers. Finally, the aggressive style is characterized by a driver who will perform riskier maneuvers, evade lanes, increase speeds, and don't take into account the comfort of the occupants. So we construct these pairs of vectors. I'll obtain them for surveys that were conducted with drivers. As shown in the table, a higher value of the weight indicates a greater importance in considered die criteria for the solution. As for the signs in the impact vector, they indicate the preference for reducing or increasing the specific criteria. The proposed path planning and selection scheme is shown in this diagram. We can observe the proposed scheme that conjuncts the 2 algorithms, path planning and trajectory selection. Then the selected path is passed as a reference to the control module of the vehicle to make the adjustments in speed and steering. Now, to measure the performance of this scheme, the following metrics we use. Efficiency. On this context, we use this metric to measure the average velocity of the vehicle in all the trajectories. The lane changes frequency and quality index, LCFQI. This metric indicates the quality and frequency of the lane changing maneuvers made for the vehicle. Then the safety is an indicator of the number of collisions in relation to the number of non-controlled vehicles, and for last, the comfort, that measures the change in acceleration made for each trajectory. The other methods used for comparison were long short-term memory. The selected model uses NGSIM database and generates a single trajectory to avoid collisions. Deep Q-learning network was also considered, which was trained with the same dataset to generate policies for decision-making in highways. So we have the 2 approach, the path planning approach and the decision-making approach, and a previous version of the proposed scheme. The scenario in which the simulations take place is shown in the figure 5. In this scenario, the controlled vehicle travels in loop with the presence of another 4 non-controlled vehicles that travels along the road. Each model releases 50 laps on the circuit. So as a quantitative results, we have this graph of the efficiency metric, where the red line is the median value, the blue box is the dispersion, and the dotted line indicates the max and mean values. As we can observe, the different driving styles, conservative, moderate, and aggressive, reach different speed ranges, with some of them having extremely different values compared to the rest. This indicates erratic behaviors. The behavior of the deep learning models, LSTM and DQN, are similar to the moderate driving style. For the safety metric, the importance of a good adjustment of weight and impactor is even more evident. This metric measures the number of collisions. So we're going slower as we contemplate with the conservative driving style, don't necessarily guarantee safety on a highway. In this metric, the performance of the moderate style is better because its configuration favors staying in a lane, maintaining a braking gap, and a constant speed. For the comfort metric, lower values are better. The importance of a poor adjustment is evident. The aggressive model with its erratic lane changes and maneuvers completely sacrifice the comfort of the occupants. Similar to the previous version of the proposed model that only considers speed, acceleration, and steering angle as criteria for the decision. The rest of the models remain in the same range of comfort. The last metric, LCFQI, shows that the maneuvers performed align with the adjustments for the different driving styles. With the model of the moderate driving style, achieving the performance similar to the deep learning proposals. So for the discussion, we have that the top-6 model with aggressive style demonstrates this unpredictability due to a specific weight and impact assigned to the different criteria. The inclusion of additional criteria refines and enhances the model performance. This is shown in the comparison between the previous version of the scheme and the new adaptive driving styles. With these new criteria, we can offer a more comprehensive understanding of driving dynamics. The deep learning models, LSTM and the QN, despite their distinct architecture, both models demonstrate the adaptability, capturing nuanced driving patterns, akin to a balance and moderate driving style. So the conclusions of this work are: a scheme based on fifth order polynomial top-6 for path planning and selection was approached, showing significantly higher safety and comfort performance with about 20% better efficiency, 30.43% more comfort, and 80% fewer safety violations compared to state-of-the-art methods. In addition to that, the main advantage of the proposed scheme is that doesn't require of the training step or large amounts of data to work. This is the pure transference of experience through the weight and impact vectors to the algorithm. So we can easily surpass these limitations. Additionally, taking into account different driving styles could enhance the performance of the vehicle in certain driving scenarios. For future work, we consider enhancing the proposed scheme for seamless integration between modules to enhance the response time of the method, incorporating new criteria associated with the dynamic model of the vehicle to make a more informed decision, and conduct experiments on a scale model to observe real-world behavior. So finally, our references are this, and thank you for your attention.
Okay, thank you so much. Very interesting presentation. Somebody have questions? No, I have questions about your slide. When you say efficiency 80%, 30%, and so on, yes, yeah. It's very high values, yeah. If so, maybe you need to prepare some patent for your methods, yes, because finally you will earn a lot of money. Do you think about this?
Yes. Well, because the metric.
Can you show one of the last slides where you achieved such great results?
Yes.
No, not this. No, not. Third from the ending. This one, yeah.
Yes. So, well,
it's
the
very
efficiency.
huge numbers, yeah.
Yes. As I say, the difference with these results is enhanced because the simulations were taken into certain parameters. So maybe that influenced the results of this model. As we see in the graphs, in specific with the safety violations, some of the models are enhanced to maintain the driver on the steering wheel. And this method is proposed to use autonomously without the need of the driver.
Okay, so think about this, yeah, because for such number of efficiency, so really maybe you can sell your results to some company or some protect your results by patents and so on. Thank you. Some other questions?
Thank you for your questions.
No other questions. So we need to finish our sessions. We're just staying in time. So it was not one first presentation, but in any case, it was just delay from the beginning. So finally, we just finished in time. Thank you so much for all of you. So program have 3 or 4, I think, additional sessions. So if you find some interesting presentations, we can visit after break some another sessions. Thank you so much. Bye.
Bye.
Goodbye. Or maybe it will be some another session. No, I think no. In the first 3 or 4 rooms. Yeah. Thank you. Bye. Goodbye.
Bye, bye, bye.